Uh, come in front, those who are at the back. No, we need to start now. Good afternoon. Welcome to today's edition of the Wednesday Colloquium. As you might have seen from the announcement notice, we are trying out a slightly different format today. We are going to have a joint colloquium by Amol and Gagan. And it's going to be on the recent result that is reported on the first observation of CP violation in baryon decay, which was the experiment was conducted at LHC. So before we start the colloquium, I have a couple of announcements to make. One of which is we have started a new institute colloquium series. This is across the 3 schools in TIFR, NSF, STCS, and MATS. So we probably will have, we are aiming for, sort of half a dozen talks in a year. The idea is to facilitate interdisciplinary discussion across these schools and disciplines. The more important thing is the first of this, the inaugural Institute Colloquium will happen on Monday, 11th August at 5:30 p.m. In the Homi Baba Auditorium. So we had to sort of plan this in a hurry. So it's the timing is slightly different. But do come, and we have an interesting speaker, and he'll be talking about how do you look for algebraic patterns in huge amount of data without really knowing much about the data. So you're all welcome. So as to today's colloquium, as I said, it's going to be on the result that came out in mid-July. But I want to say a few words before we start, primarily to illustrate the unique strength of TIFR, just to describe to you how this came about. So in mid-July, when this article was published in Nature, I saw this article, and it so happened that within 24 hours, all the leading news outlets had picked up this story. New York Times, Scientific American, and our own Hindu, Vasudevan Mukund, had an article in the Hindu. The title of these popular articles were quite eye-catching. For example, the Hindu title said, the CERN collider has major clues on why about the universe's bias against antimatter, and the New York Times title was New Clues to How Matter Outlasted Antimatter During the Big Bang, etc. So this piqued my interest. Then I just sent a mail to our particle physics colleagues, both experimentalists and theoreticians, Gagan, Rajdeep, Shilpi, Govindo, Amol, Tuhin. And the response was very prompt, and I think Gagan responded in an hour or so. Tuhin followed soon after. Tuhin said, "Yeah, it's nothing big. We kind of expected it." But he also, to his credit, he pointed out that what was really interesting was the experiment. The challenging aspect was the experiment, the detection of this. So that is what Gagan will talk about. But then Tuhin also forwarded to others who might be interested. Rishi, Neelmani, Sauman. And apparently he told me the Neelmani had worked on this a while ago. So unfortunately he isn't here. Otherwise he would have also talked about this. But anyway, the point is, it was within 2 days we finalized the date of the colloquium, the speakers, and everything. So I am so thankful to our colleagues here, Amol and Gagan, who were forthcoming, and then quite readily agreed to give this talk. So what we are going to do is, Amol will begin. He'll talk for 15 minutes, and he will provide the context and the background of this whole thing. Then Gagan will describe to us about the experiment, what was challenging, and how did we finally measure this asymmetry. And Amol will come back again for 5 to 10 minutes to discuss the implications. And then we'll throw it open for discussion. So that's what we are planning to do. And I'll hand it over to Amol now. So Amol, take it away.
Okay. So thanks, Manoj. So this is some new experiments Manoj has been trying after he has taken over as a colloquium coordinator. Let's see how this goes. Anyway, so as you see, there are two questions in the title. Why does the universe prefer matter over antimatter? And the second is, has the recent LHCb result cracked this cosmic puzzle? So the first thing that I try to do in the first part of the talk is to show you the connection between these two things. The first is that we seem to have a lot more matter than antimatter in the universe. In fact, almost everything that we see is matter. By that, I mean positive protons surrounded by negative electrons, but we almost do not see negative antiprotons surrounded by positive positons at all. And the question is, why does this happen? On the other hand, is this result that came a few weeks ago, which says observation of charge parity symmetry breaking in baryon decays. And for those of you not in physics, perhaps half of these words are completely unknown. So I try to make a connection between how to go from here to here in my first 15 minutes.
So who will call their matter? Who will call their antimatter?
That is my next 15 minutes. Anyway, so since you asked the question, the answer is familiar things are called matter, and therefore proton around electron going around that is what we call as matter.
Then already you have a bias.
No, that is my bias in language, not bias in physics. I'm talking about bias in physics, not bias in language. You'll understand this when you go. Okay, so firstly, I want to convince you that antimatter actually exists, okay? Because otherwise it will simply be a language, right? So positron, which is the antiparticle of electron, was actually discovered in 1932 by Anderson. This is an experiment in which you see a track of positron turning left in a magnetic field. If it were an electron, it would be a particle which would have turned right. Okay, so this assures you that antiparticle of electron exists, which is positron. Antiparticle proton is antiproton, which would have again exactly negative charge, same as proton. All other properties the same. This was seen in an experiment in Berkeley by Chamberlain and Segre in 1955. What you see here is antiproton coming in, hitting a proton, and when these two annihilate, you get many particles that go in various directions. Because showing that this actually was a p bar collision involves measuring of energies and momenta and showing that this is actually a p bar collision. Okay, both of these actually got Nobel Prize. We also have antimatter. So CERN, in fact, has an experiment going on for a very long time. This is in what is called as a LEAR, low energy antiproton ring, which produces antiprotons. There's a xenon jet. This antiproton actually makes an electron-positron pair, brings the positron along with it.
Antihydrogen as a antiproton and a positron, is that the?
Yes, so antihydrogen is a negative proton with a positive electron going around it. Okay. This is what we call antimatter, and this is to assure you this has been actually created. This, what you see, is antiproton with positron going around it. Okay. So we are very sure that antiparticles exist. Okay. This is just a simple way to show it. There are, of course, many other interesting ways too. This is a standard model of particle physics. Now, you perhaps have seen a more compact version of this, okay, but I like to show this model in particular. These three columns that you see are what we call as three generations. Each generation has two quarks. You can see up and down, U and D. Second generation has charmed and strange. Third has top and bottom. Okay. You will see that I have put, instead of one up quark, three up quarks. And that's because quantum chromodynamics tells us that all quarks come in three different colors. So you should actually consider these three as different particles. Okay. This is our familiar electron, okay, which has no color. This is electron neutral. And this pattern gets repeated in all three generations. What is to be noted here is that for every elementary particle that we have an antiparticle. So for up type quark, we have a up antiquark. For a down type quark, we have a down antiquark, and so on and so forth. The colors of these are normally chosen so that they're exactly opposite of the color of this red, cyan, green, purple, and blue, yellow. But that just our imagination. I could have called them instead of red, blue, and green, I don't know, Pratap, Ravi, and Vandana, and things would have worked exactly the same. Yeah, those three names that I give. Yeah. So what matters is that for every particle is an antiparticle. For electron, I have a positron. For neutrino, I have an antineutrino, and so on. Now, for the rest of the talk, you will need a basic convention of what a baryon is. And baryon is simply something that consists of three quarks of three different colors, so that the red, blue, and green, again, in our imagination, give you a colorless object. We also use a word called meson, in which case I have a quark and an antiquark. And since these colors cancel, these can form a color neutral object, which will be called as a meson. Okay, this is our basic language. So antimatter,
different color.
They are different. Quarks and antiquarks are different particles. They have different charges.
Yeah.
Yes.
It has to be two different bodies. It was the same.
Yes. So this is red, and this is in something anti-red. When I say cyan, it's anti-red color. Red, anti-red gives you neutral. That's again physicists' way of imagining that they form a color neutral object. No, they are not the same quarks. This is U and this is D bus.
They are not the same.
Yeah. Okay. So yeah. Sure.
Color and the opposite color. What is this way?
So quantum chromodynamics described in terms of a symmetry called as SU3 symmetry, and color simply is a charge of this SU3 symmetry. Okay, so it's a purely mathematical object. It's just that the analogy works so nice that physicists use it all the time. Okay, color simply means the charge of strong interactions. I think that's the way you can.
It doesn't have that.
Yes. Yeah. So electron, for example, does not have color. That means it doesn't have charge under strong interactions, which means that electron does not undergo strong interactions. So that's again another way of understanding physics by the color of anything which has color will undergo strong interactions. Anything which is white will not undergo strong interactions. Okay. So now that we know that antimatter exists, the problem happens to be that it is extremely rare. Okay. So here, of course, within some 15-20 you see one, but the ratio that we see is much more extreme than this. So I will use the words matter and baryon interchangeably and call it as B. Antimatter and antibaryon used interchangeably, and that's often called as B bar. Now, if you look at the number density of baryons in the universe, it is about 5 times 10 to the minus 10 times number density of photons in the universe. You will think, oh, that's actually very small. However, even compared to this, number density of antibaryons is 0, typically 0. I think I won't put a number on it, but more than 10 orders of magnitude less than 0. Okay. So what this means is for every 10 power 10 photons, currently we have about 5 baryons and essentially 0 antibaryons. That is what is said by C, only matter and no antimatter.
So this 10 orders of magnitude less, is it an experimental result or a theoretical?
It's experimental result. It's an observational result.
Can you say what?
So, okay, I fail in this answer, but I think this is again by looking at cosmic rays, looking at the fact that if there were antibaryons, there would have been annihilations happening some part of the universe, and you will see X-rays or gamma rays coming. So all of these combined give this limit. CMB.
The mindset is just looking, you know how many photons there are in the CMB.
No, that is okay, but antibaryon.
Antibaryons we do not see. That's why I say antibaryons you basically only have a upper limit, okay, because we do not see lots of values.
You mentioned this in cosmic.
Yes.
The highest of energy is not 10 to the power minus 10, 10 to the power minus 16.
Yeah.
So overall, the estimate of that, that's
okay. So yeah. So now, of course, one would think, no, why such widely different numbers? And there's a way to understand this, which is that baryons and antibaryons can actually annihilate to give photons. Okay, many other things, but finally giving you into photons. So imagine some part in the early universe where the number of baryons, antibaryons, and photons were sort of similar, of the order of 10 power 9, let's say. Okay. So for every 10 power 9 photons, Let's say there were n number of baryons and n minus, I just said 5 number of antibaryons. So that number of photons, baryons, antibaryons was approximately the same. Now, because of this small difference, n minus 5 antibaryons annihilated with n number of baryons, and that gave you some number of photons, a few times 10 power 9 photons. Okay. So therefore, then you get about, what is left over is about 10 power 10 photons, 5 baryons, and no antibaryon. So that's a very simple-minded picture of what would have happened. So this tells you that in early universe, the asymmetry could be small. That's perfectly okay. But main important thing is it is non-zero. So somehow the asymmetry has to be there. I think that is the main lesson that you get from this.
Is there a reason why the order of photons and baryons are the same here in the example you took?
See, in the early universe, temperatures are so high, you don't really care why it is a baryon or a proton. That's why I took numbers of the same order of magnitude. Yes.
How are these experiments a property of the universe and not a property of some local part of the universe and just a property here? Why is there not another part of the universe where there's an anti-amol talking where antimatter is more prevalent than matter?
Because we see cosmic rays coming from far away distances, as far away as megaparsecs and gigaparsecs and so on. Yeah, cosmic rays and photons that we see actually come from the other end of the universe, whatever, at least from about 14 gigaparsecs away. Right? So therefore, we know that it's not a part of only our part of the universe. Cosmic rays, yeah, cosmic rays.
Cosmic rays at the highest limit, I mean, and for example, grade 3 energy, they're almost the dominant component is galaxy. Then you go to me, it's starting to transition to extragalactic. And the highest of energies, you have the GZK cutoff.
Yes.
A few 1 gigaparsec, you're not seeing any cosmic ray beyond that.
Photons, you are saying.
Yeah.
I said cosmic rays and photons, yes.
But people have looked for evidence that other parts of the universe have are antimatter dominated and so on. There would be evidence like domain walls and signatures of all of that, and enhanced annihilation signature, and they've looked with gamma ray data also, and they're not currently there are only upper. But it is conceptually possible that as a part of the universe, this happens to have more antimatter instead of matter, and something happened. I mean, there are people.
But you would see gamma rays. Annihilations give you gamma rays, and therefore anywhere matter and antimatter comes together, you will perhaps see those frequencies. Yes.
Make a change in the photon, whatever state.
No, the number to compare is not this. Number to compare is this with this. Yeah. When I say baryons exceed antibaryons, I don't compare with number of photons is simply used as a normalization factor. Yeah. Yeah. Yes.
We're saying there will be some places, then there will be an excess of photons because of annihilation.
Yeah.
But through these numbers, it's a very small compared to the total.
Yes.
The excess also will be.
Yes. So indeed, so if I see 10 power 10 galaxies of baryons, okay, I'm just giving a big number, okay. Maybe it's possible that there is no one galaxy of antibaryon flying somewhere, but we have never seen any signal of such a thing. Okay, and that's why this number is 0.
That we are talking about gamma ray photons versus this is all photons in the CMB, including CMB. At lower temperatures, you just have no photons.
May I suggest that we move on because we have left a lot of time for discussion towards the end, but we need to.
Yeah, you include that time into my.
Go ahead. Go on.
Okay. So how can we create this asymmetry? Assuming that Big Bang seems to be very symmetric, we don't have a reason to expect asymmetry. So assuming that, what would have produced the asymmetry during the evolution of the universe? And that's the question that we have. So Andrei Sakharov was the one who first listed 3 conditions that he said have to be satisfied. One is the violation of charge-parity symmetry, and what the symmetry is, I will tell you in a while, along with what's called a charge conjugation symmetry, which also I will describe. Second condition is that baryon number should be violated. And third condition is that the universe at some point of time must have been out of equilibrium. Okay. So we will see whether these are satisfied or not. But first thing we'll focus on is the charge parity symmetry.
Like a current, shouldn't you replace baryon number violation by either baryon or electron?
You wait till the second part of my talk. The talk after, which comes after Gagan's. I will talk about that, and I will actually ask you for your advice when you come to that part, since I see you sitting here. Yes. Okay. But because of baryon asymmetry, Sakhara talked about baryon asymmetry and therefore baryon violation. Okay. Because if it's not violated, then why should there be any asymmetry at all? If everything is the same, even number of baryons and antibaryons should be the same. In fact, all of them might annihilate and we would go poof. Right? Something has to be different. Initial conditions are the same, so rules have to be different, right? That's the way we look at it.
Why both CP violation and mention some incident also. Can you explain why you require both conditions?
So it is possible that interactions might change left-handed particles to right-handed particles. So for spinless particles, it's basically C violation. For particles with spin, it is CP violation. If you go to antiparticles, I'll come to that. All of this is coming. You just have some patience. Okay. So the first step is to understand what is parity violation. Okay. And that basically the question of whether our laws of nature are mirror symmetric or not. What does this mean? Suppose I perform an experiment here and I put a big mirror at this point. I film the experiment from a camera here and I film the experiment in the mirror. Okay, and I give you both these films and you should be able to identify whether this was a film taken in the open or through the mirror. If laws of nature are not symmetric under parity, then you would be able to identify these two. And a very natural assumption till almost 1956 was that laws of nature are symmetric under this interchange, because electromagnetism, which was the most familiar interaction we have, is symmetric under left and right. Okay. So in 1956, Li and Yang were the ones who proposed that it is indeed possible that the laws of nature are different as compared to left and right at fundamental level. Madame Wu actually performed this very famous experiment in which she had a cobalt nucleus with spins aligned in a particular direction. And what she observed that when this cobalt 60 undergoes beta decay, the number of beta particles going opposite to the direction of spin was more than those that went in the direction of spin. Now, if I had seen this reaction in the mirror, I would have observed that now this, because spin analogy only goes that far, that the direction of spin would be reversed, but the electrons go in the same direction. So if you look at what's happening in the mirror, you will see that the spin of cobalt nucleus is downwards and more number of electrons are going in the direction of electrons. So clearly, this observation is different from this observation, and we only see this, and this tells you that there is parity asymmetry in the universe. Neutrinos happen to be the one that break it maximally. All the neutrinos that we see in the universe are left-handed. If you do parity inversion, they will become right-handed, and we do not see any right-handed neutrino in the universe, and that tells you that neutrinos violate parity maximum. Okay. However, if we allow for antineutrinos, which are charge conjugates of neutrinos, we actually do see right-handed antineutrino. Now, this tells you that perhaps when you do a parity transformation and change the charge conjugation, then you come to a stage where symmetry is maintained. This is called as the CP symmetry. And once parity was broken, the next step of everybody was, okay, maybe parity was broken, but if you also apply operation of charge conjugation, it will be restored. So charge conjugation, just to be precise, means positive charge go to negative charge. Parity takes left-handed particle to right-handed, and CP takes particle to antiparticle. Okay, so the guess was that maybe C and P are broken, but a particle will go to antiparticle and maintain the symmetry. How does this happen? And this is an interlude. This part is a painting by Escher. I don't think Escher cared about CP violation, but he made this nice picture called Day and Night. And some of us actually found out with Tobias and I that you can change this picture, make it a parity by using a mirror, charge transformation by changing black to white, happens to be black and white picture, and then you do parity and charge conjugation. So you come here and you see these two pictures look alike, almost alike, but not entire. Okay? This is not physics. You can have a look at this picture later. What's important is that in 1964, Cronin and Fitch showed that this assumption was not true. Even CPE is violated. So what was the first experiment that did this? They identified two mesons called K and K bar, which were CP conjugates of one another. So this is D S bar, this is S D bar. Okay, so they are conjugates of each other. Now, if you are able to form a superposition of them, which is K minus K bar, this will have odd CP. Okay, so its eigenvalue will be -1. If you do K plus K bar, it will have even CP. Turns out that these particles decay into either 3 pions or 2 pions, and also ends up that 2 pions have even CP, 3 pions have odd CP. Therefore, if you observe that Kl always goes to 3 pions and Ks always goes to 2 pions, that means that CP is conserved. So that was the essential part of this experiment. So you can see it here. You produce red and green, which is odd and even CP in equal measures. Even CP particles decay very soon. So green goes to green, that's perfectly okay. Red goes to red, that's perfectly okay. CP is conserved. What was observed was that very far away, you still see 2 pions. Okay. Now, this could have happened in two ways. One is that this red went to green, which meant a CP odd K went to CP even K, which is a CP violation. Another possibility is that this all the way was a CP odd K, but this went into CP even final state. Either of this means the CP is violated. Okay, so this experiment therefore proved that CP indeed was violated. Whether it was violated like this or like this was not shown by the experiment. That was shown much later by experiment at one of them was KTEV, on which I worked for a year. So that is why that's close to my heart. But this told you that CP is violated. The question now is, when can you see CP violation? Violated is fine, but we should be able to find out experiments in which that is. Okay. So CP violation means amplitude of x goes to y is different from amplitude of x bar going to y bar. X bar and y bar are the CP conjugate particles. Okay. So observability, the mod squares of these should be different because what we measure is not amplitude, but we measure cross section, which is proportional to mod square of amplitude. This we all have in quantum mechanics. Now comes the trick thing. What you do is to go from x to y, you identify two paths. One path I called as T, other path I called as P. Okay, so I can either go in this direction or in this direction. Okay. So I got amplitude through T and amplitude through P. Okay. So for these two, I can write the tree amplitude as some magnitude times phases, which are delta T and phi T. And for P, I got a magnitude delta P and phi P. The difference in delta T and phi T is that if I go from particle to antiparticle, delta T does not change sign, but phi T changes sign. If I can identify such processes, then I'll be able to do something. And the reason is, I can actually now calculate what happens to x goes to y, which is the sum of AT and AP. If I do mod square, I get expression that looks like this. If I look at the second process in which the antiparticle exposed to antiparticle of y, I get something like this. And now you notice that there is a difference in this last term, which if I use my trigonometry, ends up having sine of phi t minus phi p and sine of delta t minus delta p. So this tells you that if I want to see CP violation, which is difference between these two rates, I must have complex amplitudes, something which has some complex part of it. This led to the theory of CP violation. So in 1972, these two gentlemen, Kobayashi and Maskawa, showed that if there are 3 generations of quarks, then the mixing can be described by a 3x3 matrix. At this point, remember there were only 2 generations of quarks were discovered. Third was not even in picture. So these people showed that indeed if there are 3 generations of quarks, mixing can be described by a 3x3 matrix, and then whichever attempts you do at getting rid of those complex phases, one phase has to remain. It's a very interesting proof, and perhaps at some point of time we can discuss that. But this provided the complex nature of amplitude that was needed for CP violation. Okay. So now we have CP violation observed, and we have a theory of CP violation that is in place. Okay. So just to put things into sort of mathematical perspective, the Lagrangian term which shows you how quarks interact in charge current, this is U, C and T quark, this is D, S and B, and this matrix that you see is called as the quark mixing matrix. Okay. Now, for CP violation, some of these terms have to be complex. So in the standard parameterization, the 2 corners VUB and VTD are complex terms. So that this happens to be like this. So this ends up describing CP violation observed in experiments so far, and there are literally hundreds of them. Most of the measurements were carried out. These are called as B factories, which specially produce B mesons, and these are experiments at LHC, one of which Gagan will talk about in detail. However, all of these experiments so far involved decays of mesons. And for the Sakharov thing to actually be implementable, that CP violation must involve baryons somewhere, because somewhere you should have association in baryons. Okay, and therefore we have to identify processes which have baryons in them. Okay. This is a process which was found and was used in the LHCb thing. You have a question before I go ahead? This is my last slide almost. Yeah.
No, previous, you said some of the elements have to be complex, but why some and not anymore?
See, it is possible. See, because quark is a fermion, in general, a phase of a quark, global phase, is undefined. Okay. So you can always change some of those phases to make some of the elements real, and there are tricks of doing that. What Kobayashi and Masukawa showed is that whatever amount of tricks you use, you cannot make all of these elements real. So that is the beauty of that 3x3 proof, which I can show you later if.
Why and not some other?
That's a convention. No. So this is in the standard convention. This is true. This is standard convention. That's it. It's a one convention that's used everywhere. This is again with expansion up to some leading order. But indeed, if we go to higher orders, all of the elements are complex.
So the magnitude of the matrix element, they remain invariant with whatever parameterization you take. But the phase, it's like the direction of the vector. So you go from one coordinate to another. So the phase you can turn around, and in the standard parameterization, it is only on the extreme. But yeah, when you go to another parameterization, they could be somewhere else. That is not the matter. Matter is only one phase, and you cannot reduce that.
I could choose them to be here and here, for example, or in 3 of them. It's my choice. Standard parameterization puts them here and here to do leading order calculations. Okay, so this is the decay which is identified. So this is the lambda B, which basically means baryon consisting of U, D and B quarks combined. This can go to proton and pions. Proton is U and D. That's what makes a proton. Pi minus is made up of D and U bar. So now you see that if I only look at quark levels, this process and this process is basically the same. If I look at initial and final state, this is a lambda B0 going to proton and pi minus. This is lambda B0 going to proton and pi minus. However, these diagrams are very different. You see, this is a W boson. This is a W boson with a loop and a gluon going. Okay, so we'll not go to calculation, complicated things. However, so this is called as tree diagram, this is called as a penguin diagram. And if you can read the vertices here, you will see the CK matrix elements written. And remember, I had said that what matters is VUB, which has a complex number, and VTD, which has a complex number. Both of them appear, and this tells you that definitely these two have different weak phases. Remember, we also needed the delta T and delta P to be different. Calculation of this is extremely hard, therefore cannot be done very well. But we expect that these two are different because this has a loop, and there are technical reasons why when you have a loop, you typically get some additional phases. Okay, so this is the way to identify these two decay modes. So same particle goes to the same two final states, but goes through different ways which have different phases. So that's how you identify. Yes. Yeah. Yeah. So these actually are of the almost the same order of magnitude. They don't differ so much in their magnitude. The main thing is that the CKM elements appearing here and here are different, and therefore these two things phi t and phi p are different. Yeah.
Type question. So this is so that I understand Madam Wu's experiment properly. If I take your bubble chamber experiment and I have a charge particle which reflects to the left. If I look at a mirror, it will reflect to the right, which only makes sense if I invert the charge. So why do you say electromagnetism is symmetric in mirror reflection? It does not seem to be.
No, because
invert the charge, it will not.
No, because when you mirror reflect, you also changing the direction of the magnetic field.
Okay. So that is
everything gets mirror reflected. Everything should mirror reflect. Okay. Anyway, so
if I have and if I have a mirror here, it has to be a very strange mirror so that it inverts the magnetic field in the other direction. Normally, the direction of the object is not.
Let's not go into. We'll draw something on the board and figure out what this is. I don't want to take Gagan's time because I have just showed how to identify, but how to measure, I think I'm going to give it to Gagan. And then, okay, maybe I'll take one question from Alan.
Just one. You might see lambda slides. Now, there is the lambda zero particle which was discovered by our guy of our colleague, Markeshwar.
Yes.
In Australia. Is that the same particle?
No. So lambda zero particle is UDS. And this is UDB. So S quark is B quark. So a different particle, but in the same nature.
Same family.
Same family.
Lambda. Lambda zero.
It's called lambda zero. Anything which is U, D, and some other particle with isospin 0 is called as lambda particle. That's the convention of the.
So, Amal,
One question. The question I asked earlier was about the second Sakharov condition. Why do I need it? The initial condition, there's n and n minus 5. Even with baryon number, the conservation at the end, I'll have 0 and 5. Why do I need the second condition?
If CP is violated, and the CP involves only mesons, never baryons.
No, but your second condition said baryon number conservation has to be violated, not CP has to be violated in baryon.
Okay.
So why do you need that as the independent?
If baryon number is violated, if baryon number is not violated,
So
you'll always have baryon number of antibaryons equal to number of baryons.
that number of B minus number of B bar have to be conserved.
It has to be 0, 0, 0.
Conservation.
Conservation means it should be conserved. In the Big Bang, it was 0. It has to say 0. Yeah. So initial condition is very important. We are assuming the initial condition is symmetric in B and B bar. Okay. So Sandeep's infleton will go to B and B bar at the same.
one question. Yeah. See, number of antiparticles.
Fine.
So number of antiparticles you create in PP collision and antiproton collision, will they be different, or number of antiparticles you create per proton-proton collision and antiproton collision?
Yes, they'll be different. Yes.
They will be same?
No, different.
I'm really lost. So the original of everything must be the fluctuation which we can instantly PSR.
Perhaps we don't. That's why I said
We don't know that.
we don't know that. I mean, the theory of inflation. There are theories of inflation, not unique theory of inflation. Yeah. So I don't talk in speculative theories. I know once I get baryons, then I'll see what to do with them. That's my principle.
Okay, so since Amal took exactly 40 minutes for me, and I will finish only 10 minutes, okay? Right, so let me start with, and first I break the symmetry. So we start with this timeline, and this part Amal has already presented, the CP, the parity violation. Unfortunately, the Nobel Prize went to the theorist, although I thought Adam would have got. And So this is the one, where the experimentalist got the Nobel Prize and the CP evaluation by Cronin and Fish, and this was totally unexpected, right? And then for the second time, again, our theory friend, sort of took our Nobel Prize. That the Kobayashi Masukawa, as Amal said, when they predicted in 73. That is the time only 3 quarks were known. So, sort of saying something, bringing in the third generation, that was really a novel idea. But then it has to wait. I mean, the experimental verification, because, to have the CP evaluation in the KM decay, you could have there's a theory of the so-called superweak and so many other models which could explain this. But then when these two gentlemen came, in their theory, you could predict, you could see similar kind of CP evaluation like KM decay, but they also predict a large CP evaluation in the B meson sector. And that is where the Babar and Bell collaboration, they confirmed in 2001. And you could see only after that experimental verification, the Nobel went to Kobayashi and Masukawa. They shared with Peter Higgs. No, I'm sorry, with now, I'm sorry. And then you can see there is the further experimental verification of CP evaluation in the charm meson sector and the beauty baryon sector. So all along it has been measured until this year with beauty baryon. Now, you just look at 2 plots, and each of the plot brought 1 Nobel Prize. So in this one, what you see, Amala has already explained. So this is that the 2 kind of kaon, k short and k long. And if CP is a good symmetry, k long should only go to 3 pion mode. And if CP is violated, k long will go to 2 pion. And you can see that this is the data, and this is the prediction for the 2 pion and the pi 0. So clearly CP is violated. Now you go to the other side. This is the plot. In fact, one of the experiments we did. So this is so-called the B meson decay. And what you see, there's 2 things you have to see. There's 2 kinds of CP evaluation in this plot. Now, if CP would have been a good symmetry, what you would have seen, the red and blue, they would have been exactly on top of each other. So the fact you see there's a clear separation, not only there is a clear separation, they follow a sinusoidal behavior. The magnitude of the sinusoidal behavior is a very important parameter. And after that was measured precisely, Kobayashi Masukawa got the Nobel Prize. The other thing you see, Amol said there is 3 kinds of CP evaluation. So this is one kind of CP evaluation. There is another CP evaluation which could have been present there, but it is not there, with the height of the blue and the red being different. And as you can see from the plot, they are pretty much same. And that is also as per the prediction. So I would summarize that sometimes experiment lead to unexpected discoveries. So that is like this one. And at some time, theory predicts what we observe with a well-planned, well-designed experiment. So now, in this kind of various experiment being done, so what is the overarching goal? Amol has already introduced the CK matrix, Kabibo-Kobayashi Masukawa quark mixing matrix, which is a unitary matrix. And what it tells that how social the quarks. There are 3 generations of quark. So the quarks, they like to talk to each other in their family. So up would like to talk to down, jump to strange and top to bottom, but they also like to crosstalk each other. But what is the strength of the crosstalking is what? So you can see the diagonal element is basically how they're talking within their family. The off diagonal element takes how they're talking to their neighbor. And this matrix being unitary, you can use the unitarity condition applying the orthogonality relation for the first and third column. You can get a triangle. And in fact, all that thing measurement that we have done that tells that this triangle is triangle. It is not squeezed to a line. And that would have been dangerous. I mean, we wouldn't have been here to discuss because all the CP evaluation content of so-called standard model of particle physics that essentially proportional to the area of the triangle. So that's the important point. So currently, all the measurements we have been doing, most of on the CP evaluation CP evaluation sector, we are trying to precisely measure the sides and the angles of the triangle. And as Amol said in response to Alok Choi's question, so it really doesn't matter. What matters that the magnitude of the matrix element, they remain invariant in whatever modeling you take, whatever parameterization. But the popular parameterization, so-called Wolfenstein parameterization, we say the phase part is kind of delegated to the 2 exterior element. So, but the important point is there's only one phase, and that you can see if that would have been 0, the triangle wouldn't have been triangle. So now let's go to the experiment of LHCb. And okay, you all know that EIFR is part of CMS, and we are not part of LHCb. But what is LHCb? It's a general purpose spectrometer, and sort of CMS and so-called Atlas, which were famous for discovering the Higgs particle. So LHCb is a forward arm spectrometer. So if you look at, like, basically you are colliding proton with proton, and these B mesons or B baryons are coming, what you see, the probability of this particle coming in is mostly either forward or backward peaked. In the what we call the central or barrel part, they're sort of very, very small. So the experimental ingenuity, to my mind, that to find out an experiment with just a forward arm spectrometer where you are just looking at the peak. I mean, you are collecting most of these events. And this is a very famous equation in experiment we deal with. Any interesting thing that you want to do, so-called controlled particle physics experiment, we deal with 3 factors. The factor number 1, what we call cross section. So that's I cannot do anything, or anybody cannot do. That is the probability of given process occurring. People like Amal, they calculate this cross section, and that we cannot touch anything. What we can do, we can work on the other 2 factors. The second factor, what we call integrated luminosity, that tells, can I enhance the rate at which this process, the initial particle are colliding? And that's certainly our accelerator friend, they can help us on that. As a detector physicist, what we need to do is so-called how efficiently, some process is happening, and I have a detector to detect. Can I efficiently detect that? Maximum you can go efficiency to 100%, and we tend to go to as closer to 100%. Now, so the second term, you see the integrated luminosity, that matters. And in LHCb experiment, what they have done, in this plot, you see the integrated recorded luminosity as a function of year, and they have used roughly so-called 9 inverse femto-1 data collected over this 2011 to 2018. And because LHCb is recording data at higher energy, like 7, 8, and 13 keV, they have access to all kind of charm and beauty hadron. So as Amal presented, so if you see a simplistic picture of colorless hadron, so-called lambda baryon, is made up of up-down, B quark. Basically, you take a proton, replace a up quark with a bottom quark. So that is lambda baryon, and it's antiparticle lambda bar. So when you're colliding proton with proton, the fact is this LHCb detector is very forward arm spectrometer. The beauty baryon comes with a very high Lorentz boost. As a result, what you see, this particle is roughly, sort of transfers almost like 2 centimeters before decay. And that property is used in the experiment. Okay, so how does LHCb detect particle? So very 3 simple concepts. One is you have charge particle, so there is a magnetic field. The fact it is a forward arm spectrometer, you need a very simple dipole magnet. So, one particle goes clockwise, up, down, and the other one will go, one goes this way, other goes opposite way. The other thing you have, there are 2 ring imaging Cherenkov detector, so which essentially uses this Cherenkov principle, Cherenkov radiation principle. Like if you have a particle passing through a dielectric medium with a velocity greater than velocity of light, you see Cherenkov ring, and that is deployed, and that's very important. So in order to do this high quality flavor physics, what we need to determine, we need to determine the momentum, energy. Why energy? I said, I mean, if you have a neutral particle, you cannot measure their momentum because there is no magnetic field effect. So that there we do so-called calorimetry or measure the energy. And in order to find the particle type, you can have 2 particles of same momentum. Unless you measure the velocity, you cannot tell which particle is what. Once you measure the velocity and momentum together, using the formula m gamma beta c, you can tell what is the mass. And the other thing, you can precisely want to measure the decay position. So LHCb is well equipped to do all these things. All right, so that is about the experiment. Now let's what they have measured. So what they have measured the asymmetry between the number of so-called matter decay, where the lambda b going to proton, kaon, 2 charged pion, and it's antimatter decay, which is lambda b bar going to antiproton, positive kaon, and pi plus pi minus. You just take the ratio, which you can just sort of see from the height of these two, the difference of the height. Of course, there this signal is presented by this red dashed line, and there are very little background. And the beauty of this experiment, when you put that, I said 2 centimeter, the lambda baryon moves almost like 2 centimeter. By putting a cut, you cut down the entire background, what they call combinatorial background. So they measure a yield asymmetry of 3.7 with plus minus 0.4. Now the question is, what we have measured, how sure we are it's not a detector effect? Indeed, the asymmetry that
Earlier number, so that basically tells you at 4%, 3.7% you have the asymmetry exists.
right. Now this asymmetry, yeah, exactly. Now whether this asymmetry is exactly CP asymmetry or something more is what goes in the next slide. So the yield asymmetry that we measure, that has 2 parts of it. That is, you can have sort of fictitious asymmetry because of physics and detector effect. So I'll go one by one. So what LHCb has measured is this AN. Now, out of this AN has got 3 components. One is the so-called CP asymmetry, which we are interested. There is a production asymmetry. The fact is we are colliding proton with proton, which has net baryon number of +2. So as a result, what you have, there is a kind of, sort of a preference for more matter. So you have the lambda b versus the lambda b bar production that is different. So there is already you are starting with a scenario where there is a little bit preference for lambda b. So that we have to correct for. The second part is so-called the detection asymmetry. Our detector is made up of particles. Our detector are made of only matter. There is no antimatter detector. Now, so these particles, like when you have pion, proton, kaon, when they interact with proton, neutron, and electron, which are basically making your detector, the cross-section has certain difference between proton, antiproton, kaon plus positive, kaon negative, kaon. So that has to be corrected for. So the second experimental ingenuity comes here, that you have to somehow find another process where you have to have the same production asymmetry, same detection asymmetry, and the CP asymmetry should be 0. So that when you take the difference, these 2 guys will cancel out. What you will remain is exactly the CP asymmetry. In fact, that is what they did. Oh, by the way, before I go there, I just wanted to say, as Amol said, that in order to have direct CP asymmetry, you need to have 2 amplitude. And indeed, there are 2 amplitude and, sort of similar rate. So what they did, yes. Yeah.
I think I told the master form, the sigma L efficiency.
Yeah.
Wouldn't you measure the efficiency separate?
Absolutely. That is already done. So after taking that efficiency thing, so you will have to correct for that efficiency being K plus K minus. That is done. Still, the cross section is different. So the K plus, when the K plus to proton interaction, the cross section versus K minus to proton interaction, that is there is a difference, subtle difference, but it is not absolutely one top of other. The fact is, if you put an antiproton, that's a different matter. Okay.
We add like the PP product at the.
So these are just this scalar quantity. So you're thinking of something like there could be some, there is no interference. So it's like you have 3 asymmetry, right? Right.
But they're kind of ratios, right?
Yes.
Like
So if you go back to this, so what one is trying to say that each of the number that you have, in that number, whether you have only the contribution coming because of, this versus this, when you are taking the difference, that whether you have exactly the coming due to the CP, or there is already intrinsically this lambda b is preferred over the lambda b bar, and whether this final state particle, when they're interacting, see you don't see lambda b parts. I mean, you see the final state, the decay product. So the decay product, when you are seeing, you already there is a inherent asymmetry, because the proton and K plus K minus, pi plus pi minus, when they're interacting with the detector, there is a difference between the particle and antiparticle, and that is.
They are small.
Yeah.
Therefore, in linear order, they can simply consider that.
That is the.
Oh, so she is saying there is a higher order. Okay.
They're small, so therefore we can just simply have three contribution.
Okay. Sorry, maybe yeah, right. Okay. Right. So now what you see, so this is what I'm saying, the experimental ingenuity. So you have another channel, what we call the control decay channel. So where you have only this so-called lambda b going to lambda c pion, there is only single amplitude. So since it is single amplitude, there is no two amplitude or interference or CP asymmetry. In this case, the CP asymmetry is supposed to be exactly 0. On the other hand, if you look at, because lambda b, there is also lambda b. So this production asymmetry should be same. So also because the final state particles are identical to what you have, the detection asymmetry is also same. So you just take the difference of the CP asymmetry measured in, the yield asymmetry measured in this, from that, and this is where you get. So you can already do the calculation. This is first observation and more than 5 sigma, right? I mean, you can just do a sort of central value divided by the error, but no. I didn't give the number. So you keep this number. There is another number which I did not give, but that is the CP asymmetry measured in this decay, right? The yield asymmetry. So in that case, you have AN is equal to A prod and A dit, because ACP is 0, right? Now, so when I take this number minus, I think maybe I should just update my slide to give what is the AN for this guy. So, but you can do the back calculation and find out what is the AN for this. Okay. So this is the ACP for this particular decay. Yeah.
There is a fraction asymmetry because it's a PP machine.
Absolutely. So it's if it would have been proton antiproton machine, so clearly the lambda b would have been lambda b number and lambda b bar number would have been same. The detector is fully made up of matter, and the cross section of the, I mean, you think there is some antimatter? I don't. At least I didn't build any detector. Right. So now you'll say, okay, you have seen this beautiful CP asymmetry. So what is the main source, right? And this is what Amal was saying. This is the difficult part. So what was done, since there is 4 particles are coming out of the collision, coming out of the decay. So LHCb has looked at different, sort of chopping and cropping. So they did a closure inspection, and what they found, the most dominant contributor to that CP asymmetry we saw in the previous slide is coming from a broad resonance. So this is the invariant mass of the pair for the proton, pi plus pi minus. So you can see there is a broad resonance over here, and that guy is really contributing the large part of the CP asymmetry. Oh, the number should change, right? I mean, because it's not one, it's, I mean, not exactly. So it's like A1, A2. So when you do, because it's the total phase space, right? So 4 body phase space. So you're looking at certain part of the phase space, and there you get a number. And when you're looking at the different part of phase space, there is some cancellation, right? I mean, and that is where the phase space, the variation of the weak phase and the strong phase across the phase space comes into play. And that is the thing what Nilmani was saying. It is very top job, and indeed it is a top job. That how do you take into account, or how do you take this variation of the CP asymmetry, largely the strong phase and the weak phase across the phase space, particularly the strong phase. But there are some theories, there are some estimate made from the old days of this pion nucleon scattering, and that reasonably matches with this. And this is exactly what Nilmani was saying, is a difficult task to measure calculate the CP asymmetry. But I'm an experimentalist. My job is to find the measurement as precise as possible. And you can see clearly, like, I mean, any blind person can also put his hand and then say, indeed, there is a CP asymmetry, right? You can see it, the height of the lambda b0 going to, that whatever, and then the antimatter of that. So this is where, so you'll say, well, we are not part of LHCb. I mean, TIFR is not. Oh, what is that resonance? You should tell me what is that resonance. No, it's a nucleon. I mean, is it called N? I'm forgetting. N or something it is called. I mean, but it's a very broad resonance. I mean, as you can see, something like I think N17 something. Maybe you can look at the PDG together. Okay, so now one question. This is just a digression, as Amol also took a digression. So this is a digression. One would say, well, we're not part of LHCb, and we're part of the so-called Bell and Bell 2. We're working with that. A natural question would be, couldn't I have done it? And the answer is no, right? So then you will say, why is that? The thing is, the lambda b baryon, the mass is 5.6. Here we're colliding 5.6 GeV. Sorry, I should complete that. At Bell, we're colliding E plus E minus. So clearly, if this collision is happening, what we call this so-called BB bar epsilon resonance, which is a bottomonium resonance, and is 100% of the time going to be meson. So we don't have enough kinetic, energy to produce this lambda b, right? So that's as simple as like that. We cannot produce lambda b. But then Bell 2 has certain advantage with respect to LHCb, particularly since it is a E plus E minus machine. It has certain advantage when you are dealing with neutral particle or missing particle. So anyway, so this is we're here talking to LHCb, and I think now we will go to the interpretation.
No, I think I want to come back briefly. Oh, you want? Yeah, maybe.
Not related to lambda b. I know what you are saying, but we cannot measure lambda b at all. But we can do the lambda c, or other thing we can measure. Lambda b, we don't have enough energy to produce the lambda.
You're saying predicting it from theory is very hard.
Yes.
But is that for doing it differential across the phase space, or the overall integrated across the phase space is also hard to do?
That probably almost should say, but more important.
It's harder for baryons than mesons? Is it much
Yes. That part I can say convincingly. The baryons are difficult. So the mesons are yes. And about the phase thing, given if you have a broad resonance, it is much more complicated to deal with. So, but I would say the inclusive asymmetry is sort of reasonably okay. But if you're doing all the broad resonance, they are very difficult. Okay, so then we go back to.
Come back. I know he will discuss the implications of this result, not just for particle physics, but even beyond.
Don't put too much responsibility on me. Okay. So now that perhaps we are convinced that CP vibration exists, we are convinced, hopefully, that CP vibration has been observed in baryons. Okay. Then we'll go forward and see what Sakharov has to say about this. Okay. So we have found this out, okay, along with charge conjugation symmetry, but that's trivial because if the CP is not conserved, then for spinless particles, charge is not conserved. So that's actually calculated forward. Let's see, talk a bit about these two. I just have 3 or 4 slides. Okay. Again, to remind people, charge conjugation is positive negative charge. Parity is left-right handed. CP is particle to antiparticle. Therefore, if you observe CP violation for spinless particles, you basically observed charge conjugation violation. So that's not a. Okay. Next is baryon number violation. Okay. Now, baryon number happens to be what's called accidental symmetry of standard model, which means that there is no fundamental principle by which it should be conserved. But when you write down all the interactions that you see at the Lagrangian level, you see that there is simply no interaction that violates baryon number. Okay, and therefore it's accidental symmetry. But of course, it's therefore only at the Lagrangian level or the perturbative level. Yes.
Did not observe the violation? That's why you derived the theory.
No, which observation?
Period number violation.
Yes.
So that's why the best of the neutrino and the massless. Based on the standard model was derived. Now neutrino has the mass, so there's the quantity.
Right.
So these also not the same.
Yes. But I'll tell you first what the theory says. This is my next thing which I just hid. However, okay, although not very popular knowledge, at non-perturbative level, there exists a solution of the electric field equation that breaks baryon number and lepton number at the same time. Okay. This solution is called as the sphaleron. Okay. This solution is actually dependent because on the topological nature of vacuum of the gauge fields. Let me not go into that. But a sphaleron solution essentially changes the baryon number and lepton number by 3 at the same time. So if you see here, this is a sphaleron, and you perhaps, I don't know if you can see these arrows going in. This is D quark, D, C, S, T, all are going in. Each of the quarks has a baryon number of 1/3. So you'll see 9 delta B going in, which means that 3 times delta B is lost. You see 3 neutrinos going in, which means that delta L is lost. So a sphaleron transition typically changes delta B and delta L both by 3. However, it turns out that the change in B minus L ends up being 0. So B minus L is conserved. However, baryon and lepton number both change. So standard model therefore has a provision for changing baryon, for violating baryon number. So Govindo, therefore, just to do that, you don't need new physics. No, so you cannot. It actually needs a very specific combination of many gauge fields at the same time. Okay. So in fact, this process, it's not a local solution. This is a non-pot, it's a global solution. So experimentally, it is very hard to target. We can talk about it later. There are these fancy ideas of being able to create exactly right number of W's and Z in the right configuration, but that's not something you can do, at least at the current detectors. Yeah. So here, this is the next step. Okay. So the spherons are effective when the electroweak phase transition happens, when the temperature is about 160 GeV. Okay. So it is possible, therefore, that along the evolution of the universe, with the temperature of 160 GeV, this could have happened. Okay. Now the devil is in the details. The details actually show us that the amount of energy that we have available at electroweak phase is grossly insufficient, and therefore in the standard model, this effect is not strong enough. You need something beyond standard model. Okay, so that's one thing. There are scenarios which I think are a bit far-fetched, which try to produce baryon asymmetry by electroweak, what's called electroweak baryogenesis, that needs phase transitions which are very, very strong. And now we know, as Shomer also some time back showed me some of those papers, which showed that the transition, electroweak is actually almost like a crossover. It is very, very weak. So this does not seem to be the way to go. Another reason that this actually happens, the main culprit is the condition, the third condition, which was out of equilibrium. Okay. Now what happens is the following. Even if you create an asymmetry, if you are in a big soup where things are interacting with each other, things will again interact with each other, the asymmetry is going to be lost. Okay, so asymmetry will be preserved only when you go out of equilibrium. Okay. Now, what happens is quarks have strong interactions and electromagnetic interactions. So therefore, they stay in equilibrium for a very, very long time. Okay. And as a result, they get a very small time to create the asymmetry, even in spite of the CP variation that we have. And that is one reason why it is not possible to create a baryon asymmetry simply by the CP variation that we saw now. There is one way out, okay, which is to use neutrinos. Now, neutrinos are weakly interacting. So they decay all early, and they can be out of equilibrium for a very, very long time. So one of the ways that people try to think is that neutrinos create asymmetry at a very, very early stage. They stay out of equilibrium. When electroweak phase transition happens, then of course there are sphalerons, and they can then convert it back to baryon asymmetry because delta B equal to delta L. So if you have something in delta L, you give part of the delta B and but this is called as baryogenesis through leptogenesis. But this is just one of the possible ways. Issue is very wide open. There are scenarios, I don't see Basu here, who written paper on this called endogenosis, which means you produce dark matter at the same time that you produce baryogenesis and so on and so on. Okay, so current thing therefore is no, we do not know is the simple answer.
So if we see in the neutrino experiment, right? So that will be a kind of litmus test of the leptogenesis. Can we say that? Or?
It will be a test, but not the litmus test, because simply having CP variation is not enough. You do need to construct scenarios in which neutrinos create those asymmetry and decouple at a reasonably early stage. Yeah.
Given that we know what's started on this also, and given that we know the exact, let's say we know the exact well enough to know it's very transition. Can't we say that baryogenesis won't do it? We need that.
I'm very happy to say that. No, I say that. I said it reasonably strongly that baryogenesis will not work. You will need something else. Okay, something else through particles that decouple earlier. It could be neutrinos or it could be dark matter. So that these are my two favorite ones.
Firstly, thanks to both of you for very nice.
I haven't finished my
clear-
talk.
Then
This is my last slide.
Then
But-
very quickly the question. To me personally, that matter exceeds antimatter, that's what we see, it's cool. But what I'm more interested in is there is a measurement of this asymmetry, and if lattice calculations cannot account for it, is it a sign of new physics beyond standard model?
No. Lattice calculation right now, it is too early to say they can't account for it. Okay. Because
If they can't, is it a sign of new physics? That's what I'm.
yeah, if they can't is a very if question. I mean,
No, the asymmetry. The measured asymmetry, you can try
yeah,
to.
that's what he's saying. CP asymmetry on lattice has not yet been calculated. There are attempts going on, but there is no calculation yet.
Does it solve
No. Huh?
the puzzle solve?
Yeah.
Okay.
Go ahead.
Yeah. So here I go to what's called Bettridge's law of headlines. It says that if any headline that ends in a question mark can be answered by the word no. Okay. So the question was a clickbait. Okay. So the answer is no. So why this talk? This reminds us, A, that standard model of physics particle is incomplete. Okay. The fact that there is matter asymmetry means that it is incomplete. Secondly, is like Sandeep said now, new physics must relate quarks to leptons or neutrinos. We right now have quarks and neutrinos, leptons as separate sectors, but we saw that featherons is the most logical way of being able to get something. And third is again something that you were mentioning, lattice calculations involving baryons, which can calculate CP are very crucial because other standard QCD methods to calculate that work for mesons reasonably do not work for baryons. Okay, and I think Nilman is actually working on some of these calculations, so that part is going to be very crucial. Yeah, and last is just this, it gives us an excuse to try out a new format for this colloquium, which was perhaps more interesting. Yeah, so that's it, now I stop. Yeah.
Let's thank Amol and Gagan once again. Those wonderful questions and for revealing the during for you. So we'll take questions now. Kedar.
Your entire discussion was really informed by sort of the gauge theory of the standard model and this fellow on them. But Sakharov was formulating his conditions long before.
Yes.
So what was his motivation for these three, the second and the third?
See, it's quite logical, no? So if you look at Sakharov conditions, they can be understood even without really knowing details of what's happening. Okay, here it is. You need CP asymmetry because you need particle antiparticle. You need baryon number violation because basically you are asking why number of protons is different from antiprotons. Okay, so therefore only something that happens in mesons or only has something that happens in photons and does not work. So you need baryon. Third is equilibrium because if you're not in equilibrium, any asymmetry that you form, because you have things are always in the quantum soup with each other, it will get wiped out. So these three conditions are simple logical conditions, and that's the beauty of it. They do not need.
They're just completely general.
They're completely general. They don't need any standard film.
Two questions. One was basically about that resonance. I didn't quite understand if you can explain it again. And whether the fact that most of this CP violation is somehow coming from that resonance area, whether that allows one to come up with simpler processes which also show CP violation. The second question is I'm still a bit confused about that lattice calculation of baryons. So can you tell what calculations are you expecting, keeping in mind that A, standard model cannot be put on lattice, and B,
Sorry,
a standard model cannot be put on lattice. chiral fermions cannot be put on lattice, and B, a calculation of strong interactions with non-zero theta parameter cannot be done on lattice.
So, Somen, the first part of the question, I didn't show and that is not the only component. So when you see the nature paper you read, there are 2 or 3 contributor. This was the largest contributor. So almost if you take in terms of percentage, it's almost like close to 70 to 80% of the total CPS unit. So there are other 2 contributor. So they are there, right?
Now, think of other processes, looking at where your contributions are coming
Right.
from. Why
Right.
that is down?
So
allows you to come up with
exactly. So experimentally, so this is the the first baryon in which this CP asymmetry is measured. So you have to look at the complementary measurement, and in order to see in some process, in some channel, that these resonance may not be there. It's kind of you have now one piece. Now you have to try to disentangle each of the effect of each of these resonance. That you can do if you do multitude of measurement where you see that one of these resonance is contributing or not contributing. So that is because now they have 4 times more data. We can go back to the slide. But so now there is kind of whole factory of measurement will be carried out. And then they can correlate this, cross-correlate the measurement to say, pin down that what is that nature.
Lattice thing, my answer is that we just expect lattice people to be ideal and calculate all kinds of things for us non-perturbatively and exactly. Well, at least this trick. No. So it's of course it's a very ambitious ask to ask. Yeah.
Okay. Any simple chiral fermion Lagrangian cannot be done.
We will move to the next question, Ravi.
So this is very live. All this is about the observable matter. All this
yes.
talk is about observable
Yes.
matter. Nothing implies at all to anything that we know what we call dark matter.
Yes. Except for the fact that if in the end, I mentioned these scenarios called ethnogenesis. So these scenarios, what they do is they create asymmetry in dark matter sector and visible matter center at the same time.
Particles are. We're still debating what the particles are.
So we don't know.
So what is anti? What is? Where is the violation? Do we know anything about what those particles are?
No, we have no idea. We only have speculative scenarios. We know dark matter exists. We don't know what it is. So we can only have scenarios.
Should be reserved only for observable.
Yes, only for observable.
Aims of getting baryon symmetry from dark matter asymmetry since 95.
Yes.
So that's David Kaplan take the baryon dark
Mhm.
Go.
Thank you very much. Very interesting. Just a follow-up from the astrophysical/cosmological perspective. So these scenarios should be possible in the early universe. So I can imagine domain wall collision is a natural consequence of such things, which will create, both amplitude and phase bifringence in pulsar timing array. So do they have any implication for what, most likely we will see astrophysical and later the SKA time. So are there any, I didn't follow the expression.
There are gravitational wave observations predicted if the electroweak phase transitions that I mentioned is strong enough. So there are.
And this observation has any implication for those? Can you?
See, one of the open questions is whether the electroweak phase transition is strong enough so that baryogenesis will work.
Yes.
Okay. If the transition is strong enough, it means that the energy exchange during that time was very strong. And the claim is that would reflect itself in gravitational wave signals that came from that phase transition.
Right.
So there are papers, I think Geraldine Savant has written something.
Right. So down the line, there should be equivalent constraints sort of coming from the pulsar timing arrays and things like that. Down the line, not now.
Perhaps, yeah.
Very difficult.
Pulsar timing array, how can solve this problem?
Exactly.
No. So we'll talk about
cheap
it.
way.
So I'm not sure whether those gravitational wave signals fall in the frequencies that are accessible to pulsar timing array.
They do.
For that we can. They do.
They do.
Okay,
domain wall collisions. The lectures from ICTS I can point.
Yeah.
So we will take the other.
So the CP phase that can be extracted from this baryon decay measurement, how does that compare with the meson decay measurements?
I can answer that. So, I was showing that unitarity triangle, right? So
Right.
there is one of the angle called gamma or phi 3, right?
Right.
So what you have, so that is mostly measured in the meson decay. Okay, so what we call B to certain transition of Cu bar S. So now that you have, so that is mostly in the meson. Now you have baryon. So you have to do the measurement of similar like B to Cu bar S, and then compare the gamma measured in the lambda, lambda B baryon with the B meson and see the consistency. So that is next working in progress.
Okay, thanks.
Any other questions, comments?
I'm going to ask a very crazy question. Gopu was, or you were also talking about, dark matter connection. But, one of the most, important problems in cosmology is what is the nature of dark energy. So does any of these things going to ever reflect upon that question?
I have not seen or done any discussion about connection of dark energy with matter antimatter asymmetry. So I have not seen. That's
Any other questions? If not, Amal, I have one to Gagan as well. So what's so this is this experiment, or what we have learned, this confirmation of baryon decay, the CP violation baryon decay cannot explain the matter antimatter asymmetry. And that is because at very early times, even though standard model predicts some asymmetry, it will all be in equilibrium, and baryons cannot sustain this asymmetry.
yes.
So you talked about this lepton sector, the CP violation lepton sector. So that is probably the answer to this. But when does that happen? Later in the age of the universe?
No, that can happen earlier. That can happen earlier because neutrinos decouple early. Neutrinos are only weak interactions. They don't have. So therefore,
But
they will.
when does it get transferred to baryons?
No, that will happen when electronic phase transition happens.
So when does that happen?
So neutrinos create asymmetry very, very early. They preserve their asymmetry because they are not interacting with anything else. But electronic phase transition happens because they are non-perturbability processes. They can actually transfer their asymmetry to.
So at what stage in the universe life does that happen? Later?
So this is temperature of 160 GeV.
So it's all early, before the first 3 minutes.
Yeah, all before. After that, you form nuclei.
Experimentally, we should first measure the CP asymmetry in the neutrino oscillation. Then the leptogenesis thing, whatever we can.
See, all happens earlier, no? After that, particles get masses and then they form nuclei, and all that thing happens much later.
So that seems to be the current pathway or solution.
That's important. Yeah. Create early universe, preserve somehow till electronic phase transition happens, and then convert. You may not require, you may not. He says yes, but I think you may not require first order transition. If it's a phasonic process, you may not require first order transition. But again, I'm not extremely certain of this that I can say.
How do you think that is?
So equilibrium is taken care of because non-equilibrium happened long ago.
But initial can also work. If I somehow had to start with,
Yeah, that's
that can explain.
yeah. So that's that's a cheap way of.
But how did that?
Yes.
How will that happen? So is that within standard
No,
model?
we don't know. You push your lack of knowledge to saying initial conditions. Right?
Okay. On that note, let's thank Amol and Gagan. There is tea in West Canteen. Please go over and we can continue our discussion from there.